Alright, so let's do some graphing of log functions, but before we graph any log functions, I want to remind you about how we graphed exponential functions, what they looked like, and kind of what some of their important properties were, because we're going to see that, or as we've seen in the past, that logs and exponentials are inverses of each other, so a lot of their properties of exponentials will apply to logs, but in a backwards kind of way. So you'll see that in a second, okay? So if we were to graph this, let's go right to graphing, okay? If we were to graph this, we would plug in any values that we want, right, for x, okay? And I'm going to just pick, like, for example, let's say -1, 0, 1, 2, and 3, right? So those are some good values. Maybe we'll get a nice shape out of this, okay? So really nothing special here. When I plug in a -1, I get 3 to the 0, which is 1. 1 minus 2 is -1, right? So I can do this for all these values, and I'm not going to spend a lot of time walking you through this, right? 3 to the first power is 3 squared, which is 9. 9 minus 2 is 7, right? When I get to the next value, I'm actually already getting a little bit too large. 3 squared, 3 to the 2 plus 1 is 27 minus 2, which is 25, right? So these values are going to be way too big for us to be able to use. So let's plot what we have and see where we're at. So I have -1, -1. Oop, let me put it in the right spot. Okay. -1, -1. 0, 1. 1 up to 7, right? And then again, 2 is like way up here somewhere, okay? So we're kind of only seeing this like straight line. So instead of this 3 value, we kind of want to, we know that the graph should kind of flatten out a little bit and kind of be a half curve. So I'm going to get rid of this 3, and instead I'm going to plug in maybe like negative, I don't know, like negative, let's just plug in -2, okay? So if I plug in -2, this now says 3 to the -2 plus 1, 3 to the -1 minus 2, right? So that's really 1/3 minus 2. 1/3 minus 2 would be -1 and 2/3, right? So about almost -2. So we can come over to -2, and we say -1 and 2/3 would be like kind of right about there, right? So we're starting to see it flatten out, okay? So I'm going to see if we can get a good sketch of this. It looks something like this. And now we got to decide what to do with this tail. And so I'm going to come over here to this question: what is the equation of the asymptote of this? To remind you about what the asymptote was, there's some line that the graph will approach, but it will never quite go through that line, right? So it's kind of like a wall. The graph starts to get close to it, and it starts to flatten out because it can't go beyond that wall. And so for us, it's going to be -2. And the reason that it's -2 is because your d value shifted the original parent function's asymptote that was at 0, right? All exponentials have an asymptote, a horizontal one right here at 0, okay? And then the d value, the transformation shifted it down 2 units, so that's going to be an equation of y is equal to -2, right? So I can kind of look at my graph now, and I know, right, that it's going to kind of flatten out along this asymptote. It's going to go right along the edge. It's never going to go below it. And this would be a good, accurate graph of my equation, right? So just to answer this final question, what are the domain and the range? If you remember, the domain, okay, for all exponentials is everything, and that makes sense because you're allowed to have any exponent that you want. There's no restrictions on that. The range in this case looks like it's from -2 and up. So y values are greater than -2, which if you remember, that also makes sense because the domain of the original parent function was at greater than 0. We shifted it down 2 units. There's no a value negative to flip it over, right? So it should stay greater than, and that works out, okay? So we're going to do the same thing, but we're going to kind of look at logs, right? So before I even get to this question about what do we pick for values, let's think about what the domain and the range and the asymptotes and all that should look like, right? So if you remember, logs and exponentials are inverses of each other, which means we switch the domain and the range, and almost everything about them is just backwards, right? So if I take a look at the questions that I asked, what are the domain and the range for an exponential? The domain was all real numbers. So when I come to my log function and I say what's the domain and range, right? So domain and range, okay? For range, I'm going to say that now is all real numbers, right? So before it was, in the exponential version, it was the domain. So for the range, I'm going to say that's all real numbers, and the domain is going to have some kind of restriction on it, okay? So we're going to think about now, well, what's that restriction? How do we figure out what values we can plug in for x? So if you remember from when we talked about solving log functions, we said we actually can't solve or simplify a log function if there is 0 or a negative number inside of the log. So we're going to focus on the inside of the log, x plus 2. This must stay positive, which means greater than 0. So if I write this out and solve it, it looks like x has to be greater than negative 2. That is my domain. X is greater than negative 2. And so that makes the asymptote that we saw in the other one, ooh, I think I missed a letter there. Okay, asymptote. Okay, asymptote. Okay. There's a P in there, okay? So the asymptote is going to be, the wall is going to be at x is equal to negative 2. So if you compare these, this one had a domain that was everything, the y value had a restriction, and that meant that there was an asymptote that was y equals. So when I come over to the log version, because it's an inverse of the exponential, the opposite of everything is true. The range becomes all real numbers. There's a restriction on the domain, which means the asymptote includes x. So here's what this means about our picture, right? So I'm going to put the asymptote down first. The asymptote is going to be at x is equal to negative 2. That is a vertical line right here at negative 2, okay? So you can see everything about the exponentials that we did is backwards, right? The domain and the range switched, the restrictions on the domain now, the asymptote is horizontal, or is vertical instead of horizontal, right? So it's very different than what we did before, okay? Now I can just graph, okay? So when I'm graphing, I actually have to be careful. I'm only going to pick x values that are greater than negative 2. So I'm actually going to start at negative 1, right? 0, 1, 2, and 3, right? So that's a good spread. Actually, I'm going to spread it out a little bit more. Instead of just picking 5 consecutive values, I know that this is going to be any value up to 10. So maybe I'll pick like, I don't know, a 5, and I'll pick a 7. Pick a 7, yeah, okay. So I pick negative 1. When I plug in negative 1, this says the log base 3 of 1, which is 0. 0 minus 1 is negative 1, okay? The log base 3 of 0 plus 2 is the log base 3 of 2, right? So I'm going to write that down. This says the log base 3 of 2, right? When I plug in a 0, this becomes 2, and it's the log base 3 of 2. If you remember from the last video about the base change formula, this is the same as the log of 2 over the log of 3, right? So that some of your problems when you're using when you're graphing a log and evaluating a log, you might actually have to go to your calculator and use the change of base formula in order to figure out what the value is, right? So I'm actually on my calculator that you cannot see. I'm doing the log of 2 divided by the log of 3, okay? Hitting enter, and I got about 0.63, right? So log base 3 of 2 is about 0.63, and then I need to subtract 1 off of that. So it's going to be about negative 0.37 would be a good estimate, okay? When I plug in a 1, it says log base 3 of 1 plus 2. Well, that says the log base 3 of 3, which is 1. 1 minus 1 is 0. So you can see that some of these, the first one and the third one, I didn't need to use the change of base formula for, because I know in my head what the exponent should be for the log base 3 of 3. Okay, so I plugged in a 5, right? When I plug in a 5, it says log base 3 of 7. So again, that's what I need a calculator for. I'm going to say the log base 3 of 7 is the same as the log of 7 divided by the log of 3, okay, the log of 3, which is about 1.77, and then I need to subtract 1 off that. That's going to be about 0.77, okay? And then when I plug in a 7, I get a 9. So this is the log base 3 of 9. 9 minus 1 is 8. I'm sorry. The log base 3 of 9 is 2. 2 minus 1 is 1. Okay, so you can see a couple of them I needed the change of base formula. A couple of them I could evaluate just knowing what the answer is. For example, 3 to the what gives me 9, right? I knew that one. Okay, so now let's graph this. Let's see what the graph looks like. Right, answer a couple questions about it, and then we shall be finished. Okay, so if I plug in negative 1, let me use a good color. Right, negative 1, negative 1. Okay, 0 goes down to about negative 0.37. 1, 0. 5, 2, 3, 4, 5 goes up to about 0.77, and then 7 goes up to 1. Okay, so you can see it's pretty flat here, and we know that when it approaches the asymptote, it's going to just dive down sharply. So this is going to kind of go down really fast, okay, and then it's going to come up subtly. Just pretend like I hit that point really good, okay, and it's going to look like, if you notice, again, let's do some comparison. It's very similar to the shape, or it's almost identical to the shape of the exponential. It's just kind of flipped over because it's an inverse of the exponential. Okay, so here are some of your connections that we just talked about. We said that logs and exponentials are inverses of each other, so that means that instead of the asymptote being y equals like it is for an exponential, now it's going to be x equals, which makes it a horizontal asymptote instead of a vertical asymptote. The y-intercept of the exponential becomes the x-intercept of the log, and the domain and the range for an exponential and a log that are inverses of each other will switch positions, because that's what the definition of inverse means. Switch x and y and then proceed from there. Okay, so you can answer lots of questions about logs. Okay, so we're going to end by taking a look at an example that looks like this and saying, like, how can I answer some of these questions without ever having seen the equation? Right? So knowing what we know about things like transformations and parent functions and the like, how can we answer these questions? So our first example, or our first question says, without graphing, what is the parent function? That just means get rid of all of your addition, subtraction, multiplication, and division, and then write what's left over. So in our case, log base 3 of x, right? Y equals, right? So that would be the parent function. That's as simple as I can make that. I got rid of minus 2, minus 6, and multiplication by 2 at the beginning. Okay. Remember, the range for all log functions is all real numbers. Okay. The domain in this case is going to be what's going to make this stay bigger than 0. So when is x minus 2 greater than 0? Well, that's true when x is greater than 2. So my domain is x is greater than 2. Okay. The equation of the asymptote is then x is equal to 2. Right. So that's what's going to make it. We're kind of saying there's that imaginary vertical line at 2. And it will never go to the left-hand side of that. It will never be less than that one. Okay. Our x-intercept. How do we find x-intercepts? Well, all x-intercepts look like some x value comma 0, right? Something comma 0. So what we know is that the y value is 0. So if I plug in it, write this equation, 0 equals 2 times log base 3 of x minus 2 minus 6. Okay. And I solve this, okay, I'm going to kind of do a lot of calculations all at once. I'm going to add the 6 over and then divide by 2. We're trying to isolate this log. So if I turn this into its kind of isolated form, it's going to say 3 equals log base 3 of x minus 2. Okay, and then I can do a log conversion here to solve. So 3 to the third power is equal to x minus 2. Well, 3 to the third power is 27. Equals x minus 2, so it looks like x has got to be 29. Okay, so I'm going to say in this case the x-intercept is the point 29 comma 0. Okay, and then to state any transformations, just to kind of highlight how transformations connect to this is an a value. Inside of the function is still c, and outside of the function is still d. So I'll just verbally say what the transformations are. It looks like I'm moving to the right by 2. I'm moving down by 6, and I'm vertically stretching by a factor of 2. No reflections, anything fancy like that, just the vertical stretch happening to our parent function.